All right, let's take a look at the lowest common ancestor of a binary search tree question from the Grind 75 question list. Given a binary search tree, BST, find the lowest common ancestor, LCA, node of two given nodes in the binary search tree. According to the definition of LCI in Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So the example they give is you've got a root node of 6 and you got 2, 8, 0, 4, 3, 5, and you have 7 and 9. And they're looking for a 2 and an 8. So if we look for 2 and 8, we can see that 6 is the lowest common ancestor because there's no node further down the tree that would contain both of them. And if we look at the next example, they have another tree and they're looking for 2 and 4. So the 2 is over here and the 4 is here. Now in this particular case, because 2 is the parent of 4 and this can be considered a descendant of itself, we can actually consider the output to be 2 as the correct answer. All right, so the constraints are the number of nodes in the tree is in the range of 2 to a giant number. The node.values are going to be signed integers basically, or some giant numbers. All node values are unique, that's important, and P does not equal to Q, and P and Q will exist in the binary search tree, and yes, we are dealing with a binary search tree. All right, so let's look at the explanation to see how we can tackle this one. To solve the lowest common ancestor of a binary search tree, we're going to make benefit that we're actually looking at a binary search tree. And just as a refresher, a binary search tree, at least in this example, whenever we look at a particular node, any node on its left is going to have a lesser value. So, 2 is less than 6 and 0 is less than 2, so on and so forth. And the same would apply in the other direction, but it wouldn't be a lesser value, it'd be a greater value, right? 8 is greater than 6, 9 is greater than 8, so on and so forth. So what does that tell us? So for example, if we're looking for the 7 and the 9, what does that tell us? If the 6 is less than 7 and the 6 is less than 9, what does that tell us? Well, we know that the 7 and the 9 are over here. If this value is less than both of those values, it means we have to go to the right. It can't possibly be on the left. So that's going to be our first case. It's on the right somewhere. And then what we're going to do is explore the 8 node, right? Because we're exploring from the 8. And from the 8, we're going to make the same kind of comparison. All right, so if 8 is less than 7, which it's not, and 8 is less than 9, which it is, well, this is wrong, right? You can see that 8 is not less than 7, so it cannot be in the right side. What about the other comparison? If we want to check out the left, so to check out the left, exact opposite condition. If 8 is greater than the 7 and 8 is greater than the 9, well, of course, that's not true. It's not on the left either. Okay, so if it's not on the right and it's not in the left, that must mean it's us, right? And that's actually the solution to this problem. So no matter which situation you find yourself in, the lowest common ancestor of a binary search tree is a node of itself. So if we had 8 and 7 as P and Q, it would be 8. Or in this particular case, where P and Q are 7 and 9, this algorithm will be able to find the lowest common ancestor of a binary search tree. Time complexity for this, as well as the space complexity, is going to be O of n, where O is the number of nodes, and same with the space complexity, because in the worst case, we're going to have to explore all the nodes. All right, let's jump into the code. First thing that I want to do is check if the root is not nil, and if the root is nil, we're just going to return nil, and I'll probably just unwrap P, Q, because we know that these are given to us optionally for some reason. And then we're probably going to have an explore function that we're going to use to explore the tree as we go through it. I'm going to delete this code up here, which is the definition of the node. It's not particularly exciting. It's the standard node you're going to see in many questions. And at some point, we're going to explore and we're going to pass in the root node to start, and we're actually going to return from the root node. So that means that this function right here is going to go ahead and return us an optional tree node. And it's going to accept a node, and we're going to type that optionally. And the reason that we're typing it optionally and not non-optionally is simply because each node that is defined here has an optional left and a right, and it's easier to handle the code that way. So first thing I'm going to do inside of my explore function is go guard let node else return nil. And then what I'm going to do now is go if the node.val is less than the p.val and the node.val is less than the q.val, what does that tell us? Remember, that means we need to explore the right. So we're going to explore node.right. Otherwise, if node.val is greater than p.val and node.val is greater than q.val, that must mean it's in the left. Otherwise, if it's not on the left and it's not on the right, it's got to be us, right? So we're going to go ahead and return node. So I'm going to go ahead and submit this, see if I made any mistakes here. Yes, I didn't actually, right, I need to actually return from the explorers here. Go ahead and submit again. And there you go.